So I want to start this video off by talking about s'mores. So what is the formula for making s'mores? Well, it's essentially 2 cracker squares, 1 marshmallow, 3 chocolate squares, depending on how much you like chocolate, and that produces 1 s'more. But what if I gave you 8 graham crackers, but you still only have 1 marshmallow and 3 chocolate squares? So you could still only make 1 s'more. Okay, what about if we had 8 marshmallows? But then I still only have 2 cracker squares and 3 chocolate squares, so I can still only make 1 s'more. And if I had 8 chocolate squares, I still only have 1 marshmallow and 2 cracker squares, so I can still only make 1 s'more. Adding more of one ingredient does not help me make more s'mores. I need more of all the ingredients. Okay, so what if I had 8 graham crackers, 8 marshmallows, and 8 chocolate squares? Well, I can't actually make 8 s'mores because I need 2 crackers, so that takes me down to 4 s'mores max. But I'm going to need 3 chocolate squares, so I can actually only make 2 s'mores, even if I have 8 chocolate squares, 8 marshmallows, and 8 graham crackers. So which ingredient limits the amount of s'mores that can be made? That would be my chocolate squares. Since I need the most of them, they're limiting how many s'mores I can make. Which ingredients are in excess or left over? Well, I'm going to have 2 extra chocolate squares. I'm going to have 6 extra marshmallows. And I'm going to have 4 extra crackers. But that's not enough to even make a single extra s'more. This is exactly how chemical reactions work. So this may seem like a little silly s'more example, but just like you can't make any more s'mores than you have the ingredients to, you can't make any more product in a chemical reaction than you have reactants to make it. And that's what we're focusing on in this video. So this brings us to talking about the limiting reactant versus the excess reactant. So the limiting reactant is the reactant which limits how much product is being produced. It's sometimes also called the limiting reagent. So in our s'more example, the chocolate was our limiting reactant. We needed more of it than anything else in order to make the reaction of s'mores happen. In a real chemical equation, unlike our s'mores example, that reactant is going to be completely used up and none of it will be left over. The limiting reagent stops or limits the reaction after it is entirely consumed. On the other hand, we have the excess reactant, which does not limit or stop a reaction from occurring. It's sometimes also called the excess reagent. So in our case, it was our graham crackers and our marshmallows because we had excess of that. And there will be excess or leftover of this reactant. It's not all going to get used up, just like we didn't use up all of our marshmallows or graham crackers. To determine which reactant is the limiting reagent, all you have to do is first convert both reactants from 2 moles or grams of the product, depending on what you're asked to do, and compare the amount of product that can be produced. The reactant that produces the least amount of product is the limiting reactant, and the reactant that produces the most product is the excess reactant. So you're essentially just saying these are my 2 reactants. You're going to do your math that we learned how to do in our previous video, and whichever one makes less is your limiting reactant, and whichever one has a larger number, makes more, is our excess reactant. So let's do an example together. You are told aluminum reacts with chlorine to form aluminum chloride. And there's the balanced equation for you. 2Al plus 3Cl2 produces 2AlCl3. If you have 34.0 grams of aluminum and 39.0 grams of chlorine, what is the limiting reactant? What is the excess reactant? So first, we need to determine the limiting reagent by finding the number of moles of the product each reactant can possibly produce. Okay. So we take our 34 grams of aluminum, given to us in the problem, take our molar mass of aluminum, like we learned to in our last video, that equals 1 mole. Then we use our mole ratio, which we got from our balanced chemical equation, 2 moles of aluminum equaling 2 moles of aluminum chloride, and that gives us 1.26 moles of aluminum chloride. Then we have to do the same thing over for the chlorine. In this case, we're using 39 grams because that's what the problem told us. We need the molar mass of chlorine. That equals 1 mole. We use our mole ratio, 3 chlorines to every 2 aluminum chlorides, and we do the math, and that gets us 0.36 moles of aluminum chloride. So whichever reactant creates less product is the limiting reactant, and the reactant that produces more is our excess reactant. So based on that, we know that chlorine is the limiting reactant. It produced less, 0.367 is less than 1.26, which means aluminum is our excess reactant because it produced more. So all you're doing is using the skills that you learned in the last video, doing it twice, and then deciding which number is bigger. So you've definitely got this. So I want you to try this one on your own. You are asked, when 3.22 moles of aluminum reacts with 4.96 moles of HBr, how many moles of hydrogen are formed? Considering the reaction below. What is the limiting reactant and what is the excess reactant? And the formula you're given is 2Al plus 6HBr produces 2AlBr3 plus 3H2. So I want you to pause this video and try this one on your own. Come back when you're done. All right, so at first we had to solve for both parts of our formula. They were a little shorter this time because we were already given the information in moles. So for aluminum, we had 3.22 moles of aluminum, and then we only had to use our mole ratio, 2 moles of aluminum to 3 moles hydrogen, to get an answer of 4.83 moles of hydrogen. Then we're going to do it with HBr. According to the problem, we had 4.6 moles of HBr. We use a mole ratio again, 6 HBr to still 3 H2, and it comes out to 2.48 moles of H2. So based on that, we know that hydrogen is going to be our limiting reactant, and aluminum is going to be our excess reactant. See, really straightforward. All right, now I want you to pause this video and try this one on your own. Except next, I'm only going to give you the answer. I'm not going to show you the work, and if you don't have the work written out on your guided notes, you're not using them on this note check. So you need to actually pause this video and actually work out the problem, and then come back when you are actually done. All right, so you were asked how many grams of aluminum sulfate are produced if 23.33 grams of aluminum reacts with 74.44 grams of copper 2 sulfate. What reactant limits the reaction and what reactant will not be completely used up? So it was asking you, what's your limiting reactant and what's your excess reactant? And then they gave you the formula, but you needed to balance it before you could move forward. So let's see how you did. You should have gotten that 23.33 grams of aluminum produces 0.4324 moles of aluminum sulfate, while 74.44 grams of copper 2 sulfate produces 0.155 moles of aluminum sulfate. So based on that, we know that our copper 2 sulfate is the limiting reactant and aluminum is the excess reactant. If you didn't get that as your answer, rewind this video and watch the instructions over again and some of the practice problems, and then try and fix your work. This brings us to our second concept in this video, which is theoretical, actual, and percent yield. So you'll remember back in our previous video, when we were doing mass-to-mass conversions, I said this was your theoretical mass, and that name would become important to you later. This is later. Theoretical yield is that theoretical mass, and it is how much product will be synthesized in ideal conditions. And that's the math we've been doing. We've been saying if everything is perfect, this is the number we are going to get. But things aren't always perfect, so we call it the theoretical yield. And this yield is determined by finding the limiting reagent and using the mole ratio from a chemical equation to determine how much product can be made. So that is exactly what we were doing in our previous video and in our previous practice problems before today. So you are already great at finding the theoretical yield. This is in contrast to the actual yield, which is how much product was actually synthesized in the experiment. This number is sometimes also called the experimental value. So it's what actually happened. We haven't dealt with that yet, but you can definitely handle it. And these two numbers bring us what our percent yield is. And this is the ratio between the actual yield and the theoretical yield multiplied by 100. It indicates efficiency. You want your percent yield to be as close to 100% as possible, that everything was as close to theoretical as possible. The farther away you are from 100%, the less good your percent yield is. So just so you have a formula to write down, percent yield equals the mass of the actual yield divided by the mass of the theoretical yield, and we multiply the whole thing by 100 to get a percentage. Once again, we want it to be as close to 100% as possible. But like all good scientists, we will never fake our data to get a good percent yield. We always have to report our results exactly how they happen. So let's look at a theoretical yield example. You are told what is the percent yield of H2O if 138 grams of H2O is produced from 16 grams of hydrogen and excess oxygen. Okay, so our first step is that we need to write that balanced chemical equation. 2H2 plus O2 produces 2H2O. You could have done that. In step 2, we're going to determine the actual and theoretical yield. Actual is given in our problem, and we need to calculate the theoretical, which you've already learned how to do. So we're going to take our number of grams of H2O, which in the case of our problem, we were told we have 16 grams of H2 as our limiting reactant because we're told excess of O2, so we know that's the number that we're going to use. So we take 16 grams of H2, we take the molar mass of hydrogen, 2.02 equals 1 mole. That means our grams have canceled out. We then use our mole ratio, 2 moles of H2 coming from right there, times 2 moles of H2O, because that's what the question wanted me to get my number in. This means my moles of H2 have canceled. And then for my last conversion factor, I put 1 mole of H2O, and then I put the molar mass of H2O up top, 18.02. This means my moles of H2O have canceled out, leaving me in grams of H2O. And when we do this, we get 143 grams. Okay? So then we need to calculate our percent yield. So percent yield is going to equal the actual over the theoretical times 100, which in our case is 138 grams given to us in the problem, divided by the theoretical 143 grams that we calculated, times 100, which gives us a percent yield of 96.7%, which is an awesome percent yield and something anyone should be proud of. I actually had professors in college that the highest grade you could get on your lab was based on your percent yield. So if your percent yield was a 60%, even if you answered all of your lab questions correctly, the highest grade you were going to get on that lab was a 60%. So professors in chemistry take percent yield very seriously. All right. In this example, you were asked what is the percent yield of ammonium, NH3, if 40.5 grams of NH3 is produced from 20 moles of H2 and an excess of N2. I want you to pause this video and try this one on your own and come back when you're ready to check your work and your answer. All right. For step 1, you should have written the balanced chemical equation. N2 plus 3H2 produces 2NH3. Then we need to determine the actual and theoretical yield. The actual was given to us in the problem. 40.5 grams of NH3 is produced, and we needed to calculate the theoretical. Now we didn't need to do both because we were told that we have this many moles of hydrogen, but we have an excess of N2, so we already know what our limiting reactant is, and that's the hydrogen. So you should have set it up, starting with your 20 moles of H2. Using your mole ratio of 3H2 to 2NH3. Then using the molar mass of ammonium, NH3, 1 mole equals 17.4 grams. Canceling our units, we are now in grams of NH3, which is what we wanted, and our answer comes out to be 227 grams. What you should have done next is calculated your percent yield. Remember, percent yield is actual over theoretical times 100, so in this case, we have 40.5 grams ammonium divided by 227 grams of ammonia times 100, which in this case is a percent yield of 17.8%. Eek! That is not a good percent yield. That usually means that something went wrong somewhere, or this is an incredibly difficult process to make happen. Sometimes even in the real world with scientists who do everything right, some chemical reactions are not very efficient and they cause you to get low percent yields. So let's put it all together. If you have 2H2 plus O2 producing 2H2O, what is the percent yield of H2O if 58 grams of hydrogen are produced by combining 60 grams of oxygen and 7.0 grams of hydrogen? So before you get overwhelmed, here's a little hint for you. Let's determine the limiting reagent first. All right, so first we need to determine our limiting reagent. So we know we want to know how many grams of water we're going to have. And we have two reagents, hydrogen and oxygen. And this time the problem didn't tell us which one was in excess. So we're going to have to solve for that, which we learned how to do earlier in this video. So we're going to take our 60 grams of oxygen, molar mass of oxygen, canceling out our grams, getting us in moles, use the mole ratio, which we got from our chemical formula, use the molar mass of water, cancels our moles, leaving us in grams of water, which is what we wanted for an answer of 68 grams. So if we use oxygen, we should get 68 grams of water. But what if we are talking about hydrogen instead? So we have 7.0 grams of hydrogen. Use the molar mass of hydrogen. Use the mole ratio. And then use the molar mass of water to get 62.4 grams. So what that means to us is our water is limited by how much hydrogen we have because its number is lower. So now we're going to figure out our percent yield. Once again, we're still using actual over theoretical, but we have to use the lower theoretical yield because that's actually the most that can be made. So in this case, we have 58 grams of water given to us in the problem. We divide it by the 62.4 grams because that's our theoretical, and multiply by 100 to get a 92.9% yield, which is a really great yield. So even when you aren't told which one is the limiting reactant, you can still figure it out on your own. All right. Here's some more percent yield questions for you. Example 15, you are asked the electrolysis of water forms hydrogen and oxygen, gives you the formula. What is the percent yield of O2 if 12.3 grams of oxygen is produced from the decomposition of 14.0 grams of H2O? So in this case, you only have one reactant, so you don't have to figure out which one is the limiting one or not, because you only have one. Example 16, 107 grams of oxygen is produced by heating 300 grams of potassium chlorate. Calculate the percent yield. And example 17, what is the percent yield of ferrous sulfide in 3 moles of iron reacts with excess sulfur to produce 220 grams of ferrous sulfide? I want you to pause this video and come back after you have worked out and shown your work in your guided notes and solved these 3 problems. Come back when you're done. All right, let's see how you did. For example 15, you did not need to find your limiting reactant because you only had one reactant. So we just should have set up our typical conversion, starting with our 14 grams of water from the problem, molar mass of water, mole ratio, molar mass of oxygen, to get 12.43 grams. When we calculate our percent yield, we put the theoretical on the bottom, what we got in our problem, divided by the actual, what we got up here, for a 98.9% yield. Great yield. For example 16, you took your 300 grams of potassium chlorate, molar mass of potassium chlorate, mole ratio, molar mass of oxygen, to get 117.5 grams, divided the actual given to us in our problem, divided by the theoretical, to get a 91.1% theoretical yield, or percent yield rather. And last but not least, for example 17, for ferrous sulfide, we were asked to find how many grams of ferrous sulfide were produced. So we started in our moles of iron this time, used our mole ratio, used the molar mass of ferrous sulfide to get 263.7. To calculate our percent yield, we put the actual, which is given to us in the problem, divided by our theoretical, which we calculated to get an 83.4% yield. And that's all there is to it. If you struggled with these last 3 problems, I recommend you rewatch this video from the beginning to help yourself out before your note check tomorrow. Have a great day.